think we're more or less familiar with forces. We have to start talking about forces and their relations to acceleration and to each other. So, we're all familiar that if I have some object, placed on the ground, I have to exert a force to push it. And clearly that this object moves in a different direction if I change my direction of force, right? So, and if I go faster, it'll accelerate faster. All that stuff's very familiar. I mean, it's just experience out of daily life. So force clearly has a size and a direction. What does that mean about it? Yeah. So it has. So force is a vector. That's the first thing we know. Force is a vector, has a size and a direction. Second thing we know is it's somehow related to acceleration, because if I push something faster or harder, it seems to accelerate more. And so we can say that there's a relation between force and acceleration. This is actually Newton's second law. Says that the relation, I have force is a vector, acceleration is a vector. There's not too many ways in normal space you can combine. You can have one vector related to another vector, except having it proportional to that vector. So force is going to have to be proportional to acceleration. And in fact, the constant, it's actually force is ma. So the forces on an object is equal to the mass times the acceleration of the object. And that's the total force on the object, is that.
So what's the subscript you put on force there?
Total.
Okay.
So that's the sum of all the forces on the object. It's going to be the mass of the object times the acceleration. That's Newton's second law. That's really what we're going to be talking about. What we're going to end up doing is writing out forces, adding them up. Since they're vectors, they're adding vectors. And just apply this. That's what we're going to be doing for much of the rest of the semester. Okay? And so, and then once you know acceleration, then you know using the kinematic equations, positions and distances that it goes, times it takes to go that far, that type of thing. And so that's really much of mechanics is doing this. So vector addition will be key in adding up the forces. Okay. Well, if this relation holds, this mass is measured in kilograms, accelerations meter per second squared. That means the units of force are kilograms meters per second squared. We have a special term for that. That's called 1 Newton. This is the SI unit, and that's symbolized with a big N. Okay? So 1 kilogram meter per second squared is 1 Newton. And that's big N here. Okay. So what are some of the forces that you guys are familiar with?
That was a kilogram what?
A kilogram
Of mass.
meter per second squared. And that's just because this equation holds, so units of whatever is on this side has to be the units of whatever's on this side. Acceleration is meters per second squared. Units of mass is kilograms. So what forces are you guys familiar with?
Like gravity.
Gravity, okay. Any others? Well, this is, much of this won't be that relevant for what we're dealing with. But there's basically four fundamental forces. There's gravity. That's the attraction between two masses. Two, there's electromagnetic forces. Three, there's the nuclear weak force, and then this is responsible for some types of radioactive decay. And then there's the nuclear strong force. This is what holds the nucleus of an atom together. All right, if you're outside of the nucleus of an atom, and by the way, a nucleus is tiny, tiny, tiny. It's 10 to the minus 15 meters across. If you're outside of the nucleus of an atom, these things, you won't ever experience these. So these are outside of our daily experience. They're very important, but they're not something that that we have any experience with just living our daily lives. So we won't worry about these in this class. So that means there's two types of forces. There's gravity and electromagnetic forces that we deal with. Gravity is, what attracts us to the Earth. Every other force is electromagnetic in nature. So, for instance, the fact that when I hit this table, and the table exerts a force on my hand, or I'm exerting a force on the table, that's at the end of the day, that's some sort of electromagnetic force. All those forces are. We'll deal with the very, very simplest of these forces in physics too. The force between atoms, when I hit things like this, that's electromagnetic in nature. That's much, much more complicated than anything we'll ever deal with when you want to get down to a fundamental level. Okay? The electromagnetic forces are very strong. Gravity tends to be pretty weak, comparatively. All right. So we can split these forces up into two other types, into maybe a couple other ways to look at them. There are forces that can act at a distance. So there's basically two that we're familiar with. Gravity, like if you jump up and the Earth will pull you back down. The Earth doesn't have to be touching you, okay, to exert a force on you. So that's a force that can act at a distance. And then there's a couple other ones that you might run into, like refrigerator magnets. That acts at a little bit of a distance. And like static electricity, you can rub a balloon, put it near your hair, and your hair will pop up. It's clearly acting at a little bit of a distance. It doesn't have to be touching. So those are, but for this class, what we'll deal with is gravity. And then the other types are contact forces. So contact forces, you have to actually be touching something in order for that force to be acting, or these are very short-range forces. And so there's basically three types of contact forces, well, in a broad sense. There's pushing forces. Like if I'm pushing on this table, I'm exerting a force on it. Those are called normal forces. There's pulling forces. If I pull on this cable, I'm exerting a force on whatever at the other end of that cable. Those are tension forces. And then there's forces like what's the stapler, you know, if I let it stop a little bit, you know, there's clearly some force when I'm moving it between the table and the bottom of the stapler. Those are friction forces. And so these are in a broad sense, these are how we'll, you know, what we'll be dealing with. One other thing before I let you go. There's a rule. This is Newton's first law of motion. If an object doesn't have any force on it, it will move at a constant velocity. Okay? An object moves at a constant velocity. That means constant speed, constant direction, in the absence of any forces. This is something that was a big shift to be able to understand this. When physics is just starting to be developed and taken away from superstition, the superstition was that you needed a force to make something move. And that, we have tons of experience with that in daily life. You know, if I want this book to be moving, I have to exert a force on it. Sitting here is actually a constant velocity, which is 0. But there are forces on it, friction and normal force. If I really had some place where there wasn't any force on it, if I just let it go, it would just keep going with whatever velocity it had and keep going forever. And that's the law of inertia. That's the big shift. And when people started to see that, then Newton's second law comes up, and then Newton's third law. We'll look at those tomorrow. Okay?